Hello there. We're going to look at this idea of descriptive statistics. We're moving from graphs that tell us something about a data to single numerical values that tell us something about a data. That's what a descriptive statistic is. A couple of important things for us here are one, an outlier and resistance measure. An outlier is a data value that's far away from the rest of the data. That's not a real precise definition. But for now, we'll go with that. When we have more measures, more statistical quantities that we can work with, we can have a more precise definition. But for now, we'll just say that it's far away from the rest of the data. A resistance measure is a statistic that is not affected by outliers. Okay. So with that in mind, let's look at measures of central tendency, sometimes called measures of location. Now these measures attempt to describe the location of the center, or the quote-unquote center or the middle value of the observed data. Now I want you to look at your text and be well aware of the three measures, mean, median, and mode. They all have various properties, and your book has an extensive list of those properties, and I want you to be aware of those. I'm going to present some of the I want to highlight some of the properties for each measure, but I want you to know that list as well. Mean, median, and mode. Something you have seen before, I'm pretty sure. But hopefully, or maybe, there will be something that's new about these quantities that we're going to consider today. The mean, also called the arithmetic mean or the average, is the balance point of a data set. Okay. Now, so how do we compute the mean? Well, if we let x be a random variable and we observe many replications of this random variable, then we can think of adding up these. That's what this numerator here represents. This is summation notation. Okay, so just as an aside, if I have x sub I and I goes from 1 to 4, this is shorthand notation called summation notation for x1 plus x2 plus x3 plus x4. Okay? Just shorthand notation for that sum. Now, so this quantity here, this is a Greek letter mu. This is actually the population mean. Okay, mu is the population mean, and the way you get the population mean for our purposes is you add up all the values in the population and you divide by capital N, which is the population size. Okay. Now, just to be clear, because this is a quantity that's computed from the population, this is a parameter. And based on what we've talked about before, recall that parameters are typically unknown because we don't have everything that we'd like to have in regards to the population. So what we can do is take a sample from a population and compute the mean. And that's what this is over here on the right hand side. X bar, X with a bar on top. This is called the sample mean. And mathematically, it's the same thing as the population mean. We add up the observations and divide by n. But in this case, we add up observations from our sample. And little n here, little n is our sample size. Okay. So, population mean, sample mean. Mu is typically unknown. X bar is what we compute, and we would like to use that as an estimate for mu. A few properties of the mean are that it's most commonly used, it actually may not be in the data set, and that it is not a resistance measure. It can be highly influenced. It can be highly influenced by outliers. So just consider with me, suppose I have 5 students in a class, and the grades for an exam are 80, 85, 88, 79, and a 15. Well, the 15 would be an outlier, and that 15 would have a great effect on what the sample mean would be. Okay? It would not be resistant to that outlier of 15. Now, I do want to come back and say something about this idea of the sample mean, or the mean is the balance point of the data. Let me give you kind of a quick example here. Suppose I have this data set, real simple data set, 1, 2, 3. If I was to kind of graph that data set on what's called a dot plot, not a real fancy graph, but you just put a dot for every data point you got. I got a 1, I've got a 2, and I've got a 3. Okay? If I was going to balance that, where would I balance that? If you could think of these as marbles, and I was to balance all these marbles, and they were on a plane, or on a board, so to speak, where would you balance it? You'd balance it at 2, and that's what the sample mean is for this data set. Right? 1 plus 2 plus 3 is 6. 6 divided by 3 would be 2. So x bar would be 2 here. Now, let me change it up a little bit. Suppose I have this data set. 1, 2, 3, 3. Okay? So my dot plot would look like this. 1, 2, and I actually have 2 3s. Okay? Now again, imagine these are marbles and they have some sort of weight to them. If I was to balance this, I would have to come out to the right of 2 a little bit to accommodate for the extra weight that's over here. And that's actually reflected if you go through and you do the computation of x bar. It's 1 plus 2, which is 3, plus 3 plus 3 is 9. So 9 over 4 turns out to be 2.25. So you would balance it over here instead of right in the middle. All right. So the mean can be thought of as this balance point idea. Okay. The above formula, this one here, is used to compute the mean when the data is ungrouped, just when we have the raw data. But sometimes we have the data in a frequency distribution, where we have it grouped. And if we have it grouped, then we use this formula to compute that mean. What do? You take the frequency of the class, then you multiply it times the midpoint of the class, and you add those little products up for every class, and then you divide by the sample size. Okay, this is not as popular as it used to be. Typically we have all the data in terms of we have our sample, and so we can compute the mean, or a computer can do it for us quickly. But this is still out there. Now, just to be clear, this is actually an approximation. It approximates the mean. Okay. Also, in terms of this idea of a mean, I want you to be aware of this thing called a trimmed mean. A trimmed mean, there's several ways to do it, or there's many ways to do it, really. You take and you lop off, say, the bottom 10% and the top 10% of the data in terms of order. So the lowest 5% and the highest 5%. You trim the data, then you take the regular mean. Or you could trim off the lowest and the highest 10%, or you could trim off the lowest and highest 20%. That's quite a bit. But when you do that, you're trimming off you're basically trimming off outliers. And so there's no outliers in the situation, and that makes the trimmed mean that makes a trimmed mean, it is resistant to outliers. It makes a trimmed mean resistant to outliers. Next measure of central tendency, the median It's the middle value within the ordered data. Okay? So you rank the data, you order it, and then the next thing you do is you find the location of the median by using this formula n plus 1 over 2. If n is odd, then this is going to be an integer, and it's pretty straightforward to find that median value. If n is even, this is not going to be an integer, and so what you do is you take the average of the middle two ordered values. Some properties of the median are that it actually may not be in the data set, and it is a resistance measure. That is, outliers don't have a great effect on the median. I'm not going to cover it here in the lecture, but the book also gives an approach to computing the median if the data are grouped. All right. The mode is the data value that occurs the most frequently The mode may not be unique. There may be 2 modes. There may be 3 modes. So it may not be unique. It's less affected by outliers than the mean. And one thing that's kind of interesting about it is from sample to sample, from the same population, the mode varies more than the mean or the median. So we say it has more variability, more sampling variability than the mean and the median. Fourthly here, it's most useful for qualitative data. When we think of the mean and the median, that's typically used on quantitative data. It is used on quantitative data. It doesn't make sense to take the average of a list of hair colors, or the average of a list of categorical variable like that. You actually can have a median involving the qualitative data, and you can have a mode for quantitative data. But it's usually not that interesting. Typically, the mode is most useful with qualitative data. So if I am interested in hair colors for students in a class, then maybe I'm interested in the most frequent or the mode hair color of all for that data set there. Mean, median, and mode. Let's look at a couple things comparing the mean and the median. Here's the data set. Okay. Now, just if we were to compute the mean here, you may want to fast forward to this part, but if you want to compute the mean, it would be x bar would be, you'd add up the observations. You'd take 46 plus 44 plus ... All those observations, the last one is 135. Divide by how many there are. Well, there's 11 observations there. That's n. If you add that up, that numerator there is 572 divided by 11, which is 52. Okay? So x bar is 52. Now the median, how do we get the median here? Well, let's see, let's have some space. I have to order the data first. Okay, so if I order the data, didn't want that to pop up. Let's see, 38, 42, so I got 38, I got a 42, I've got a 43, I've got three 44s, let's see if I can get, right, there's a 43, there's 3 44s there, I've got two 45s, a 46, a 46, and then 135. Okay, so I have 11 observations. So the median is the middle ordered value. All right, so I'm going to go out to the 6th value there. So 1, 2, 3, 4, 5, 6. This guy right here, 44, is my median. Median is 44, x bar is 52. Alright, so x bar is considerably bigger than 44 when we think of this data set. In fact, x bar is bigger than every data point except 135. What's going on here? Well, what does this suggest? The sample mean being so much larger than the median. That suggests that there is probably a quote-unquote right outlier or a large outlier. That is, there's a value that is much larger than the rest of the data. And that's clear. We see that here with 135 being the right outlier. Okay, when we think of mean, median, and mode, we can, let's see here. They can be related. There can be a certain relationship with the mean, median, and mode that corresponds, not always, but often enough to highlight it here, that corresponds to a particular shape. So here are some typical relationships. They're not hard and fast, but typical relationships. Now, if we have a right skewed data set, so if it would look like this, the right tail would be pulled over there. When we think about, okay, how might the mode, median, and mean be ordered? Well, I set it there for you in that order. Here's the mode. The median would be the value that is, it would actually here be just a little bit to the right of the mode. It would be the value such that 50% is less than that value and 50% is greater than that value. So if you want to think of area under the curve, try to find that point here. And the mean would be further out towards the right tail because it is, the mean is the balance point. It has to accommodate these values that are far out in the right tail to balance this distribution. Now this may be a little exaggerated, but the point is that if you have a right skewed data set, usually you're going to see the mode is less than the median, and that's less than the mean. And you might imagine if you had negative or left skewed, something like this, that the mean is over here, the median and the mode are ordered in that way. Okay. Now, it turns out that this is always the case, that if we have a distribution that's unimodal and symmetric, it's always the case that the mean, median, and mode are the same thing. So we see something like this. The mean is the same as the median, which is the same as the mode. Okay. The mean, you would balance it here in the middle, all right, because it's symmetric. The median, 50% of the data is less than this point, and 50% is greater than. So that's where the median would be. And mode is the highest point, the most frequent value. According to this plot there, it would be right there. Okay. There are some exceptions to the first two inequalities that were presented. Here's just a couple of them. Suppose we have a bimodal distribution. It's approximately symmetric, but it's not unimodal. All right, it's got two modes, and you see there that the modes are on the left and the right of the mean and the median. Okay, so the mode is not the same as the mean and median there, so there's an exception there. Here's kind of this funky distribution that's really trimodal. It's got a mode here, here, and then it goes down, then it comes back up, a mode over here. That would force the mean to be way out in the right tail of the distribution, and the mode would be here, and the median would be here. And so that's not really right skewed. It's hard to describe that with just one word. The picture tells us a lot more than just saying it's left skewed or it's right skewed. I mean, it's trimodal, with the largest, remind me later, with the largest mode in the middle there, and a mode close to it to the left, and then a mode way out in the right there. Okay, it's highly unusual, but this would create an exception to the rule here. Okay, now because of these exceptions, it's better to look at the histogram in terms of thinking and other graphs displaying shape, instead of just trying to order the mean and the median, and then using that to inform what the shape of the data looks like. Okay, descriptive statistics, numerical measures of central tendency.